you
This
can do
conference will now be recorded.
with instruction-based sampling. And that's kind of the main focus of the talk today. But I think Yuhong will also talk a little bit about his use case. I also want to mention that Yuhong has won a couple of awards in the system community, so he's got a good background to kind of dive into this. All right, Yuhong, take it away.
Thank you. Okay, let me
And
share
and
the screen.
we should qualify one thing, Yuhong. Can people interrupt you and just ask questions online?
Yeah, so please ask me. You can interrupt me anytime if you have a question. Yeah, okay. Thanks, Daniel, for the introduction. So yeah, today I will talk about the limitation of PAPS refund when using it to track memory request for a specific type of tiered memory, and also how this generalized to other type of tiered memory. So the specific type of tier memory we were looking at is called two-level memory. So maybe let me briefly talk about what two-level memory is. So it is a type of memory tiering scheme where the memory controller decide which cache lines stay in the fast memory tier. So like any memory tiering system, we have a fast memory tier and a slow memory tier. So for example, the fast memory tier can be DRAM and the slow memory tier can be Opting persistent memory or in the future CXL. So ideally, all the we want to leave all the hot cache line in the fast memory tier and leave the other cold cache line in slow memory tier. But in two-level memory, the cache line demotion and promotion is decided by the memory controller, not by the software. And the key difference between software memory tiering and two-level memory is that the data can be migrated at the page granularity in software memory tiering. But in 2LM, the data migration can happen at the 64-byte cache line granularity. So we already have, so the only available two-level memory we have is Opting. So Opting persistent memory, they provide a memory mode in which the DRAM becomes a direct map cache for persistent memory. And in the future, we might see similar two-level memory in CXL. So in that case, the fast tier will be the local memory and the slow tier will be the CXL attached memory. So so if you look at Optim memory mode, DRAM is a direct map cache for PMEM. And because it's direct map, such 2LM system may have severe conflict misses if two or more hot PMEM line are mapped to the same DRAM line. So for example, if we assume a 4-to-1 mapping where four PMEM line are mapped to the same DRAM line, and if two of them are popular, then they might have a lot of conflict and evict each other from DRAM, which can cause a lot of what we call 2LM misses. And in an experiment, we find that 2LM misses can degrade application performance significantly, and tracking them is important to diagnose and improve the performance of two-level memory. And so there are several mechanisms we can use to track 2LM misses or in general any mean memory request. So for example, we can look at the access bit in a page table entry, or we can use PTE poisoning to use page fault to track memory accesses. And we have PAPS, which is an acronym for Processor Event-Based Sampling. However, if you look at 2LM or in general any tier memory system, we actually just care about the mean memory request. So if you look at the memory requests that are handled by the CPU cache, they are less relevant. And among these three options, only PAPS can track only the mean memory request. So let me tell more about what PAPS is. So it's a hardware sampling mechanism available on Intel CPU, and it can be used to, for example, sample the data linear addresses that trigger certain event. So here are some events that are relevant to your memory. So for example, you can sample the data linear address that are associated with the retired load instruction that missed the L3 cache. So that means these load instruction result in mean memory request, and we are able to get a data linear address associated with that. Or we can sample the retire load instruction that missed the local memory. So in that case, we can actually know like which data linear address caused DRAM misses and caused access to the slow tier. Or we can just simply sample any retired load instruction. So because of that, we can use PAPS to track mean memory requests or even just 2LM misses, the access to the slow memory tier. And PAPS is only available on Intel CPU, but AMD has a similar feature called IBS, instruction-based sampling. So I think recently they also provide L3 filtering, which allow you to only track mean memory request. So after getting all the PAPS samples, we can aggregate those samples to get their per page LC miscount and 2LM miscount. So for example, we can aggregate the sample to see like how many 2LM misses have happened on each page. So basically, for each page, we can get the number of miscount of them. And this is very useful because this can help us identify the page that have high 2LM miscount, and which can also help us understand like where the most misses happened, and that also indicate how we can reduce the 2LM misses. So maybe we need a larger DRAM, or there are some conflict that we can resolve by moving pages around. So before jumping into the experiment result, I want to point out at a high level what the limitation of PAPS we got into at the end. So if you look at the PAPS events, all of them are all of them are directly related to memory instruction. So the problem is PAPS can only sample the mean memory requests that are directly triggered by memory instructions. However, there are other type of mean memory requests that are not directly triggered by instruction. Instead, they are generated by the CPU cache. So for example, we have CPU cache write-back, we have CPU cache prefetch, and read for ownership. So read for ownership will happen if, for example, a load instruction missed the CPU cache. So in that case, the CPU cache need to do read for ownership to read the data from the main memory before doing the store operation. So all these three types of main memory requests cannot be sampled by PAPS. So PAPS can only be used to sample the main memory request triggered by memory instruction. And later I will use an example to show why that's problematic.
Please feel free to ask questions and pause Yuhong at any point.
Yeah. And this is actually not specific to PAPS. So IBS, the instruction-based sampling available on AMD CPU, they have similar issue because all this processor-based sampling mechanism, they are more instruction-based. So they only look at the events that are directly related to the instruction. But if you look at main memory requests, we also care about the request generated by the CPU cache, for example. So yeah, so let's look at the experiment results. So we used the tool. So we built a tool to count the number of use PAPS to count the number of 2LM misses and mean memory requests of each page and see how the distribution look like. So the workload we are looking at is the spec workload. So it's, I think it's a benchmark that includes some, for example, scientific compute workload and a graph processing benchmark. And because Opting is the only available two-level memory, so we use Opting in our experiments. And we set the DRAM to PMEM ratio to be 1 to 2. So what we find is that many realistic workloads have very skewed QLM misdistribution, which indicate that they suffer from such QLM conflict. So, for example, if you look at the graph on the left, the x-axis here is the cumulative number of DRAM misses, and y-axis is the cumulative amount of memory. So the way to interpret this graph is to look at the tail. So what the tail of this graph tells us is that 5% of the pages contribute to 82% of the 2LM misses. So almost all the 2LM misses concentrate on these 5% of the pages. And we see a similar trend in the graph on the right. It is less skill than the other workloads, but we can still see that 5% of the pages contribute to 34% of the 2LM misses. So so based on this result, we think that because the 2LM misses happen on these few pages, so we might be able to resolve this conflict by moving pages around. So the intuition is that we can resolve conflict by doing page exchange. So for example, if we have two popular PMM page that are mapped to the same DRAM page, so these two PMM pages will cause a lot of 2LM misses because they are conflicting with each other. And at the same time, we might have another pair. Yeah,
Sorry, I had a question. So you're basically saying that because it's direct mapped, that you're causing this conflict. Is that what the assertion is here?
exactly. So
Okay.
because the associative direct map, so this is quite problematic. And we were
Okay.
trying to use PABs to address this issue, but at the end we find that because of the limitation of PABs, we were not quite able to do that.
Okay. Thanks.
Yeah. So if so we have a pair of popular PMM pages that are conflicting with each other. And if at the same time we have another pair of code code PMM pages that do not generate a lot of conflict, what we can do is we can exchange one page from each pair so that the popular pages won't be mapped to the same DRAM pages. So in that case, we might be able to significantly reduce the number of 2LM conflict. So to do that, we implemented a page exchange syscall. So basically, that allow us to exchange the physical page frame of two virtual pages. So using this tool, so we apply this page exchange technique in one of the workload in the spec benchmark. So it's a GCC workload. So it's basically like using GCC to compile itself. And so we see that if so we measure the completion time on the different setting. So for example, we measure the completion time when the DRAM size or the local memory size is 100%. So in that case, all of the data can fit into DRAM. So this is the best completion time we can get. And we also measure the completion time if the local memory size or the DRAM size is 50% of the resident set size. So in that case, only 50% of the data can fit into DRAM. So we can see that the completion time is significantly higher when the DRAM ratio is 50%. And
Yuhong, I'm being a little bit slow here. So could you go back and explain what the exchange actually does? I mean, and how it helps. So can you go back to the previous slide for me?
yeah,
So,
so yeah,
sorry, the one more slide up. The one where you have the PTEs and you're kind of
right.
swizzling the physical pages with the PTEs. So
Mhm.
what are you trying to accomplish by doing this swizzle here? The
Yeah,
PTEs.
so Right. So for example, if so I think this slide might help explain that a little bit. So for example, here we have, if you look at the first pair of PMAM pages, they are both popular, but they're both mapped to the same DRAM pages. So that caused a lot of conflict.
Okay,
But
I see.
if we are able, yeah, so if we are able to do page exchange, then we can make sure that like popular PMAM pages won't be mapped to the same DRAM location.
Okay.
So
Okay.
Yuang, how do you actually map? How do you know that there is a direct conflict? I'm assuming you are using platform 2LM, and you're trying to do this through the user space program. So
Right.
how do you detect that there is a conflict?
Yeah, that's a good question. So that's why we need PAPs. So we use PAPs to sample the 2LM misses. So PAPs, if you look at the list of events, so the second event allow us to sample the load instruction that missed the local memory. So that means the load instruction that ends up in PMAM.
PMM, right, right.
Yeah. So and
So
that
you're using the
and
load instruction.
right. So we actually have the data linear addresses, so we know exactly where this conflict happened.
Right. So you will know where it's coming from.
Yeah.
Let's say if it is coming from the first 2 pages.
Uh-huh.
But how do you still know? How do you know that these 2 pages are actually mapping to the same DRAM page?
Yeah. So we do that by looking at the page table. So that tells us the physical addresses. And in Optin, we know the mapping between PMM and DRAM. So by looking at the physical addresses, we know which physical addresses are mapped to the same DRAM location.
I see. Okay.
Yeah, the mapping function is fixed. Is a modular function. It's very simple.
Right, right. Okay, okay.
Yeah. So if we use PAPs to count the number of 2LM misses on each page and use page exchange to make sure that popular pages won't conflict in DRAM. So if we use that technique, we see that we can reduce the slowdown by roughly 50%. So basically in the experiment, we exchange 15% of the pages with the highest miscount with some random pages. So we can see that the completion time is significantly lower. So in this workflow, we actually get pretty good result. But what we find is that it doesn't always work. So for some workloads, even though PAPs indicate that almost all the misses can be resolved by page exchanges, we still cannot get a significant performance improvement. And this is because, as I talked about a little bit before, PAPs does not track certain type of mean memory request. So let's look at such an example. So this is another workflow from the spec benchmark. And we use the PAPS tool to count the number of LLC misses and the DRAM misses on each page. So let's first look at the graph on the left, which is the LLC miss distribution in a virtual address space. So the x-axis is the virtual address space. So that's basically the page index in the virtual address space. And the y-axis is the cumulative number of LLC misses. So LLC misses, they means mean memory request. And so what we can see is that almost all of the LLC misses happened in the highlighted hot red region. And we see a similar pattern in the DRAM miss distribution. So if you look at the graph on the right, the x-axis is again the virtual address space, but the y-axis is the cumulative amount of DRAM misses. So again, we see that almost all the DRAM misses happened in the highlighted hot red region, which we call the hot region. So we see that actually 99% of the LLC misses and DRAM misses happen in the hot region. And the size of the hot region is actually less than the half of the resident set size. So recall that in our experiment, the DRAM to PMEM ratio is 1:2. So which means that roughly 50% of the data can fit into DRAM. So what this means is that because the size of the hot region is less than the half of the resident set size, they can actually fit into the DRAM. So in this case, it's possible. So if we look at this result generated by PAPS, we might think that it's possible to resolve all the misses by putting the hot region in DRAM. But what we find is that this is actually not the case. So what we do is
Can you explain one question I have in the previous one or this one? So what exactly is the x-axis? Index in the virtual address space means what? Can you explain that?
Yeah. So so basically what I do is so the index in the virtual address space is the page index in the virtual address space. So we scan the page table and get all the mapped virtual addresses and
Right.
sort them in ascending order. So that's what we do. So because we do that because there are some gap in the virtual address space and we want to skip those gaps.
I see.
So we only look at the mapped pages.
Only the mapped, okay. Got it.
So so in this experiment, what we do is because we already know the hot region. So at the beginning, when we started running the workload, we modify the page table. We're doing page exchange to make sure that the pages in the hot region won't conflict in DRAM. So in that case, after doing all the page exchange, any page in the hot set in the hot region won't conflict with another page in the hot region. So we see that and we also measure the completion time. So what we see is that even if we make the hot region conflict free, the completion time is still quite far away from the optimal completion time where all the data can fit into DRAM. But another thing we observe is that if we again looking at the DRAM distribution in the virtual address space, even if we make the hot region conflict free, we still see a lot of 2LM misses in the hot region. So what this indicates is that because now the hot region is conflict free, so the only possible explanation is that it conflicts with the pages outside the hot region. But if we look at this graph, the pages outside the hot region do not seem to generate a significant amount of DRAM misses. So what we can conclude from this graph is that there are, so in the cold region, they must have some 2LM misses that are invisible to PAPS. So PAPS is not able to capture those 2LM misses.
Johan, can you explain this graph a little bit? So
Right. Yeah. So the blue line is if we set the DRAM ratio to 50%. So in that case, only half of the data can fit into DRAM. And the orange line is the DRAM distribution if we make the hot region conflict free. So a hot page won't conflict with another hot page. So in that case, because if you look at the blue line, almost all the 2LM misses happen in the hot region among the hot pages. So ideally, if we make the hot region conflict free, we shouldn't see any 2LM misses.
Right.
Oh, have you done any other experiments to verify that hypothesis that these references invisible to PEBs that are creating this?
Yes. Yeah. Let me go into that. So basically, as I mentioned before, there are many different types of main memory requests. So we have read requests and write requests. So write requests, they are mainly because CPU cache write back, or they can because of non-temporal store. And even if you just look at read requests, we have regular read requests and read for ownership request. And within the regular read request, we have demand regular read requests that are triggered by load instruction. And we also have some prefetch regular read requests. And PABs can actually only sample the demand regular read request. And for this workload, we actually measure the breakdown of all these main memory requests. So what we see is that it's true that there are a lot of demand regular read requests, but it's only 49% of the main memory traffic. So if we use PABs, we basically ignore a significant portion of the other type of main memory request. And we also see that although the code region, it only has a very tiny 73 gigabyte of demand regular read requests. So that's why we don't see any PI misses in this figure outside the hot region. So it's true that it only has 73 gigabyte of demand regular read requests. The cold region, it has like 500 gigabyte of other type of main memory requests, which cannot be captured by PABs. So this is the evidence that lead us to the conclusion that PABs is not quite sufficient to help us understand TLM misses, because a lot of these main memory requests cannot be captured by PABs.
So, Yihong, sorry, I have to drop soon, but I did have one question. I mean, to me, there's a higher level discussion to me about whether, to me, a lot of the things that you're talking about are ramifications of the direct map cache, and that what would happen if you had, like, even a 2A set associative cache, how many of these issues would become less magnified? Not that it would go away 100%, but if you had a different cache implementation, that maybe some of these artifacts would be less worse than they are now. Did you do any kind of assessment along those lines?
So we didn't do any experiments on other type of cache, but I believe this can generalize to other type of tiered memory. So for example, the other type of popular tier memory is software-based memory tiering, where you use either the operating system or the application to manage the page placement in the fast tier and the slow tier. So basically, in that case, the OS decides whether a page should be placed in the fast tier or the slow tier. So in that case, the OS need to have this hotness information. They need to know which page is a hot page, for example. So in that case, we still have this problem because, for example, if a page has a lot of CPU cache write back and a lot of prefetch requests, but it doesn't have many DRAM, doesn't have many demand regular read requests. So if you just use PABs, that page might seem to be cold, but it is actually a hot page and should be placed in the fast tier.
Yeah,
So,
I agree with that. If you're saying that, okay, we're not capturing all of the memory accesses by strictly looking at PEBs, then I agree with that statement. I just meant in terms of the performance benefits you're seeing here, a lot of them are an artifact to me of the direct map caching. The instrumentation, what you're gathering, I agree that what you're saying, but just the overall expected benefit is specific because of this direct map cache implementation.
yeah, exactly.
I want to jump in and also point out the main point here is to actually point out the limitation in the methodology of hotness tracking. And hotness tracking you want for a lot of other use cases, like not even just page movement. You also want it for debugging. You also want it for observational studies. So that is the main point. It's just that you won't happen to look at this one use case of it where he saw, like the problem or the limitation of PEPs actually skewed the result and made a big impact. But I think the high level point we deduced from Yuhong's research was that we need some hardware hotness tracking. That is kind of the high level story.
Sure, I get that. Okay, that makes sense. Well, thanks, and sorry I have to drop, but I would like to stay, but I can't. So
Yeah,
thanks,
that,
Johan.
yeah,
Thanks, Brian.
thank you.
Thanks, Daniel.
So Johan, can you please go back to earlier slide?
Mhm.
So if I look at this slide and the bottom left, not this one, that flow chart. Yeah, this one, correct. So PEPS captures only this demand regular read requests. Now we are talking about the main memory here. So even if, let's say, the discussion, this whole discussion started in with the context of CXL memory. We want to track hot pages on CXL memory, right?
Yeah.
So even if we look at this slide and say now we want to track requests that are going to CXL memory,
Mhm.
I think the same argument would be valid, right? Even for
Yeah.
CXL memory.
Right. So in that case, we also want to look at, for example, the write request and the prefetch request that reach CXL, not just the demand regular read request.
Yeah, 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 yeah. So that was the main point. If any of you are following this hotness tracking discussion, we started with some kind of a software interface for hotness tracking to be implemented in a CXL memory controller. But there was a argument that which is the ideal place, whether it's a CPU sock or the CXL memory controller. And Yuhong's work is trying to highlight limitations of this one of these PEBs based tracking. Uh, so that does not mean that it cannot be done if CPU sock has some other different way of adding this new hotness tracking that can be done. But at this point, we see limitations. Right?
It would also be very interesting to hear from CPU vendors if you think this is overcomable. Like that would also inform the discussion.
Right. Yeah. I think Manoj is talking. Manoj, we cannot hear you. Manoj, can you hear us? Yeah, some audio issues. I guess it.
Okay, I think there was another request from somebody from SK Hynix who was looking for some recording on hotness tracking. I'm sure he's able to get that. And
Oh, this is from the prior meeting, Samir?
prior meeting.
Okay. Okay. Yeah. Don't know if all the recordings have been posted. Need to double check.
Yeah. So let me add again. Uh, Let me show a couple of slides because many of the people might not have attended all the calls. So can you make me
Right.
presenter for a minute?
Yeah. Give me a second, Samir.
Hey, thanks, Johan. Very
Thanks,
useful in this
Rajan.
case.
Yeah. Yeah. Very insightful.
Maybe before we do that, the read for ownership requests. Can you say more about what's generating those? I thought that, if an instruction that wants to do a write is clearly going to generate a read for ownership, and therefore I would say that is, tracked by PEBs. I can see that if it has that data already in cached as read, um, then that might be discovered later and could generate a read for ownership. But that's not really going to memory. That's just a cache coherence management operation. So can you say more about what those operations are and why they're not, you think they're not being tracked by PEPs?
Sorry, I missed the first part of your question. Could you repeat that?
I thought that read for ownership would be part of a an instruction, a write instruction, and would be tracked by PEBs in general. And that there are cases where the cache might already have the data encached with read ownership, and and then might discover it needs to upgrade to write ownership. Okay, and I can see that would be an operation that would be generated not necessarily based on an instruction, but again, I view that as a cache coherence management operation, not actually going to main memory to get the data.
Right. So so in the slide I showed before, we only measured the amount of read for ownership that actually reached the main memory. So that's not just like promoting from a read-only copy to a writable copy. So that's not just the cache coherency traffic. And it's true that we can use PAPs to track the store instruction, but the issue is if we track all the, oh, for example, if we sample all the store instruction, we don't know which one um, results in main memory request. So like in two-level memory or in any tier memory, we only want to look at the store instruction that actually ends up with main memory request. So for now, PAPS doesn't have such capability. So I think that's the main problem here.
Okay. Well, I can certainly see that prefetching could generate read for ownership things as well. But okay, thanks.
Yeah.
So Johan, have you tried the other benchmark that you indicated? I think you mentioned it was Graph or AI benchmark. Or is it
Yeah.
purely spec and trade so far?
Right. So I didn't show that in the slides, but we see a similar behavior in the graph processing workloads. So basically, if you just look at the DRAM misdistribution or the LC misdistribution, it kind of indicate that all of the hot data can fit into DRAM, but after trying that, we find that there are a lot of invisible main memory requests. So we still cannot get a large improvement.
I see. So you're basically pointing out two meta themes, right? One is the monitoring capability to get visibility into what's happening. And the second thing is the actual page placement decisions using direct map is not that effective. Is that
yeah, the second one is the use case we are looking at. So we try to
which is a use case, right?
Yeah, the use case.
Okay.
So question I have is, Meta team came here and presented, right? So
Fairly similar theme. Yeah.
yeah, but did they use PEBs or something
Yeah.
else?
Yeah. PEPs plus, the Linux kernel, sysfs interface to essentially stitch together, basically a combination of hardware plus, the kernel counters to be able to get the visibility of page tracking and the hardness tracking.
Do you mean TPP?
Yeah,
TPP.
TPP paper. Yeah. And the overhead, right? So if you were to do this in the software, the real-time nature and the overhead and the aspect of by the time you say it is a hot, and then, if the workload is fairly active, there is an element of, the transition from the hot to the warm could be fairly fast, right? So there is an element of overhead, taking up the CPU cores to do this. If you were to implement this in the software, those are all the reasons.
Hey, Reddy, can you please make me presenter?
Yeah. So any other questions to you, before Samir?
Oh, I have a question.
Go ahead.
Yeah. I think that the PAPS is fundamentally based on the counter-based operating scheme. So normally in considering about the miscount, but I'm wondering how's the overhead over the PAPS scheme. I think that normally counter is tightly linked to the each page table for considering either promotion or demotion at the aspect of miscount handling. So I think this is a little bit, the overhead is not negligible at this case. So how do you think about that?
Yeah, so the overhead of PAPs depends on the sampling frequency. So if you want to get accurate data and use a high sampling frequency, and that's can result in high overhead. So the overhead mainly can come from the fact that so PAPs they have a buffer which is used to store all the PAP sample. So when the buffer is close to full, the CPU core will generate a performance monitoring interrupt, and the interrupt will be handled by the PAPS interrupt handler to copy, like to drain all the PAP sample from that buffer. So that's if we so basically if you have a high sampling frequency, then you will also have a higher um, interrupt frequency, which can cause high overhead. So yeah, so I think if you use a very extreme sampling frequency, the overhead can be like 10 or 20% slowdown.
Oh, okay, I see. Thanks for your clarification.
Thanks, Yihong. Samir, go ahead.
Yeah, so I'm presenting my screen here. So this is bringing back discussion where we started, right? We talked about why we need to add hotness tracker, and then this particular picture we all looked at together, right? There are two places for hotness tracker. One is inside the CXL memory controller, or the picture on the right is inside the CPU sock. And today's presentation from Yuhong is one attempt to tell what are some of the limitations of existing implementations on the CPU sock side. And uh, if if there are some other somebody has done work on rest of the CPU base, for example IBS or anything with the ARM CPU, I think it would be interesting to look at that data as well. So that will complete, I think, all pointers in this direction. So just to go back to the last point, right? Why we want to add this in CXL memory controller? So these are some of the main reasons. It gives us flexibility across different CPU vendors and families. So even if it works for say IBS but does not work for CPU, so that's the flexibility point, right? And again we are keeping it independent of implementation through this OCP work. We are mostly focused on the interface, and then it also gives us flexibility around when people build systems. You might have CXL 2.0 CPU and 1.0 controller, or 3.0 CPU and 2.0 controller. So it gives us flexibility around mixing and matching CPUs and controllers. So that was another point. The third one, we talked about this. CPU is ideal place for cold tracking. Uh, I do not know. I wrote this earlier, but we need more data to support that. And the another point that Reddy was mentioning earlier was CPU cycles are consumed even if you do it in some work in software. CPU cycles are consumed on running on tracking these algorithms. So that's another reason why we would like to have it in a hardware. And the final point is on, let's say tomorrow we move to CXL 3.0 memory sharing cases. Then hotness tracking becomes even more complicated, right? First of all, now that memory is shared between two CPU sockets, and whether you want to move, that's the first question, right? So you may not decide to move in that case, but even if you want to move, then which is the ideal place? Because individual CPU's hotness tracking is only looking at that traffic. You're not getting complete visibility of the entire traffic that is coming to that shared memory region. And for that reason, CXL memory controller makes an ideal choice. So these are some of the reasons. Looking forward to any other contributors who can add some more data in this area.
Thanks, Samir. Yeah, this reinforces the need to do this in the CXL
Yes. So looking forward to
device.
anyone else wants to look at some other methods such as IBS or I don't know what method is there for ARM CPUs. So if somebody has looked at that, I think that would be useful.
All right. Yeah.
Okay, great. I think
Thanks,
that's
Samir.
all.
Yeah, I think we planned only this topic today. So is Jeff on? I was wondering if we can actually do the DMTF Redfish, the preview of the Fabric Manager models next CMS meeting.
We should be able to. We're trying to get things out by Friday, so I won't know until Friday if they'll be out or not. I mean, the data
I
models
see.
are out, so
Okay.
that's there, but the presentation that goes along with them.
Okay, I see.
Yeah,
So Jeff,
so,
yeah, keep me and Manoj posted. Maybe Friday, if you can let us know.
okay.
See if we can cover for next week. That will be great. I'm assuming you're coordinating with your Intel counterparts, right? I saw the email last week
yeah,
or a week before.
yeah.
Okay, awesome. Thanks a lot, Jeff.
Right.
Any other opens for today? All right. Thanks, everyone. Have a good rest of the day.
Thanks.
Bye
Everyone.
bye. Thanks.
Bye.
Thank you.